So therefore, what we have obtained by taking numbers U1, T1, U2, T2 in this order as it's in this line, where everything else is a strict inequality except T1 can be equal to U2. This joint probability is actually equal to the product of this individual marginal probabilities. So what we have achieved by this is that we have been able to convert a joint probability about S1 dash and S2 dash into a product of marginal probabilities about the N dash process. Now the advantage of N dash process is that we have already used the independent increments, but it also has another advantage is that the increments are stationary as well as Poissonian. So let's use it now. So obviously N dash U1 is Poisson with parameter alpha times U1. N dash of T1 minus N dash of U1 is the number of phone calls in this interval, which is again a Poisson random variable with parameter alpha times the length of this interval, which is alpha times T1 minus U1. Similarly, this guy is the number of phone calls in this interval, which is Poisson random variable with parameter alpha times U2 minus T1. And this guy here is the number of phone calls in this interval, which is again a Poisson random variable with parameter alpha times T2 minus U2. Now we have to compute these probabilities. All of them are Poisson random variables with known parameters, so it's very easy to compute. So a Poisson random variable with parameter alpha times E1 taking a value 0 has this probability. Similarly, this probability is equal to this. This is the probability that a Poisson random variable with parameter alpha times T1 minus U1 takes a value 1. Again, this one is Poisson random variable taking a value 0, where the parameter is alpha times T1 minus U2. So, alpha times U2 minus T1. And then finally, we have this probability where this is a Poisson random variable with parameter alpha times T2 minus U2, but you have to compute the probability that it takes a value at least 1. Now, how do you compute the probability of at least 1? You just compute probability of 1 minus the Poisson random variable taking the value 0, because a Poisson random variable, if not 1 or more, it has to take the value 0. So therefore, by computing the complement probability of the complement, and 1 minus that, will compute this guy. And this happens to be the probability that this Poisson random variable takes the value 0. So 1 minus that is the probability that the Poisson random variable takes the value at least 1. Okay. So this gives all the probabilities. And after simplifying, we'll see that, for example, this will cancel with this thing, this will cancel with this thing here, this will cancel with this thing here, and so on. So we'll be left with alpha times U2, which is here. Okay, this U2 is there. And alpha times T1 minus U1 will come from here, and rest will be this guy here. So that's a simplification. So what we have obtained is for U1, T1, U2, T2, satisfying this string of inequalities, the joint probability of S1 dash and S2 dash, this particular joint probability of S1 dash and S2 dash equals this number here. Okay. Now, of course, the next step would be to guess a joint probability density function, which will always abbreviate a PDF, the probability density function. So we have to guess a joint PDF of S1 dash and S2 dash. Of course, the question is how to do that. Note that we have done such things in probability theory too, except that maybe we have forgotten it by now. So let's quickly recall what to do here. Let's recall what happens in the one dimension. Okay. Suppose, so this is a small digression on one dimensional case. Suppose you are, instead of giving this joint probability, I gave you this marginal probability of S1 dash being between U1 and T1 to be equal to this guy, okay, which is equal to this and which is in turn equal to this guy. Then how would you guess the PDF a PDF of S1 dash. PDF is not unique. That's why you will always write a PDF. How will you guess a probability density function of S1 dash? And the trick is to understand that for any S positive, of course, S1 dash, S1 dash has, we know that S1 dash has range positive. So for any S positive, your guess would be the density would be the derivative of the cumulative distribution function of S1 dash. If you write it longhand, this is nothing but the limit h going to 0 of the cumulative distribution function evaluated at S plus h minus the cumulative distribution function evaluated at S divided by h. Of course, this has to be limit as h goes to 0, but if the limit exists, we are anyway guessing it. So we can as well just take the limit as is going to 0 plus. Once we make h positive, the advantage is that this probability in the numerator is basically the probability that S1 dash lies between S and S plus h. But here there's a strict inequality on the left side, on the right side you have a weak inequality. Now that exactly falls under this framework where you have to put U1 equal to S and T1 equal to S plus h. Okay? If you do that, you will get this quantity here, which is obtained because this U1 is S, so that gives you this quantity. This part gives you this quantity. On the other hand, if T1 is S plus H, then T1 minus U1 is H. So this gives you 1 minus alpha H. Okay? Now note that this has no H in it, so this will come out as a constant in the limit. And this limit, this particular limit here, this part without this thing, just this part, this and this, will give you an alpha. 1 minus e power minus alpha h divided by h, as h goes to 0, gives you alpha. So this gives you this quantity. So this tells us how to guess a PDF from a probability like this. Same thing can be done in 2 dimension as well. So recall that we had computed this joint probability for all U1, T1, U2, T2 satisfying the string of inequalities. So therefore, and we also know, by the way, that the joint range of S1 dash and S2 dash is S1 less than equal to S2 and S1 is bigger than 0. S1 and S2 are both positive and S1 is less than S1, S2, right? Is less than equal to S2. So let's take just an S1 which is bigger than 0 and S2 which is bigger than S1. Let's take such S1 and S2. S1 equal to S2 won't have any role to play here because there will be a joint density. Okay? So let's just take this thing and let's try to make a guess. So our guess would be from the one-dimensional case, you just have to take the limit as H1 and H2 are both going to 0 of this joint probability divided by H1, H2. So in other words, what we are doing is we are computing S1, the probability of S1 dash and S2 dash being in a rectangle, and then divide by the area of the rectangle. Very small rectangle, and divide by the area of that very small rectangle. And very small is taken care of by these limits. And of course, again H1, H2 should just both go to 0, but we are just taking them go to 0 from the positive side so that the computation becomes easier. Okay, so now once you know that H1 and H2 are both positive, you are in this framework, and then you can just put T1, sorry, you can just put U1 equal to S1, T1 equal to S1 plus H1, T2 equal to S2, and U2 equal to S2, and T2 equal to S2 plus H2. Okay, so U1 should be S1, T1 should be S1 plus H1, U2 should be S2, and T2 should be S2 plus H2. If you do that, put the values in there, you're going to get simply this thing, because alpha will remain alpha. T1 minus U1 would be this minus this, which is H1, so that will give you this H1. Then this guy would become e power minus alpha S2, because U2 is equal to S2. Okay, U2 is simply S2. And then here also, T2 minus U2 will give you H2, because T2 minus U2 would be S2 plus H2 minus S2, which is H2. So you're going to get this thing. Now, of course, H1 will get cancelled. Okay. H1 is going to 0, but it's still positive. So you will get, that will get cancelled. And then the limit with respect to H1 is gone because this has no H1 in it. Now, this alpha and e power minus s alpha s2 will come out as constants. And then you have to evaluate this limit just as H2 goes to 0 plus. And we know that this limit is alpha. Last time we did this, we didn't do the calculation, I just stated it. It's a very easy limit to compute. So you can just say that this is, check that this is alpha. So therefore, this will become alpha squared times e power minus alpha s2. So therefore, our claim is that S1 dash and S2 dash has a joint PDF, H of S1, S2, which is alpha squared times e power minus alpha S2, as long as S1 is bigger than 0 and S1 is less than S2. 0 otherwise. By the way, the form of this expression doesn't have any S1 in it, but of course the range has it. So clearly S1 and S2 cannot be independent. That cannot be, because S1 dash and S2 dash cannot be independent here, because S1 dash is strictly less than S2 dash. Okay. So therefore, we have this joint density. We have made this claim and we have to prove it. And of course, I should mention that S1 equal to S2 line, even though I was initially writing S1 less than equal to S2, now is gone. This is because we will prove that it has a joint density. And once it has a joint density, anything one-dimensional with a probability 0. So therefore, we can as well write the strict inequality. But still, we haven't proved the claim yet. We have to prove this claim. Now let's try to understand what we need to prove this claim. What we need to do to prove this claim. All we have to do is we have to take any rectangle R which lies above this S1 equal to S2 line. So this is the 45-degree line going through the origin. Okay. For such a rectangle R, we have to show that the joint probability of S1 dash and S2 dash being inside R is given by double integral over R of H S1 S2 ds1 ds2. Okay. This would be enough. So you take any rectangle. So in order to have this rectangle, the rectangle is U1 comma T1 cross U2 comma T2. So here you take S1 between U1 T1 and S2 between U2 T2. You get this rectangle. Note that we are not allowing U1 and U2 here. So in other words, in this rectangle, these two sides are not there. These two sides are there. Now, why does this rectangle completely lies on this side of the S1 equal to S2 line? That's because T1 is less than equal to U2. Because of that, one can very easily check that this will lie completely on this side. Okay. So this is the point T1 comma U2, and T1 is less than equal to U2. So therefore, it has to lie on this side of this line. Anyway, so all we have to do, we have to take a rectangle on this side and show that the joint probability of S1 dash and S2 dash belonging there is given by this integral of H of S1 S2 on R. Why is it so? This is because if you take any other rectangle and want to take the integral on that rectangle and show the thing, then what would matter is this green part. The integral will get reduced to an integral on this green part. And the probability also will get reduced to a probability on this part. And then this part can be approximated by many, many rectangles, union of many, many rectangles, all of which will lie on this side of S1 equal to S2. So therefore, if you just show whatever we have to show on rectangles which completely lie on this side, that's enough. Because any other rectangle you take, essential part, the contributing part, which is the green part here, is going to be approximated using union of many rectangles, which are all on this side of this line. We have done such a thing in probability theory 2, but I just reminded you of that once more.